Imagine sending a high-definition video from Mars to Earth in just minutes instead of waiting hours, or even days. Right now, every image from our rovers, every byte of data from satellites crawls through invisible bottlenecks in deep space. Radio signals, the backbone of communication for more than half a century, are reaching their limits. NASA's own estimates suggest that today's spacecraft generate 10 times more data than current systems can smoothly handle. But a breakthrough is emerging that could change everything. Lasers, streams of coherent light, are poised to become the new language of the cosmos, transmitting information with fiber-optic speed across the void of space. For humanity, that means our future in space could be as connected as life on Earth. If you want to stay ahead of the future of space communication, subscribe, like, and turn on notifications. What's coming next is nothing short of revolutionary. The story of space communication is as old as the space race itself. In the 1960s, NASA's Deep Space Network was designed to pick up faint radio whispers from spacecraft like Voyager and Apollo. Those signals traveled billions of miles, bouncing from dish to dish, carrying humanity's first digital fingerprints across the solar system. But the amount of data was modest. A handful of photographs, short bursts of telemetry, basic readings. At the time, that was enough to thrill scientists and inspire the world. But fast forward to today, and the challenge is exponentially bigger. Satellites stream terabytes of climate data. Space telescopes like James Webb capture images so detailed they could fill entire libraries. Mars rovers roll across alien terrain collecting more science in a week than early missions gathered in years. Tomorrow's spacecraft will be streaming immersive video, real-time diagnostics, and vast experimental datasets back to Earth. The old system, radio, just wasn't built for this traffic jam, and the cracks are already beginning to show. This isn't just a technical bottleneck, it affects everyone. Slower communication means longer delays in scientific discoveries, which slows breakthroughs in medicine, climate science, and materials research. In a crisis, like an astronaut stranded on the lunar surface or a spacecraft malfunctioning near Mars, those delays could cost lives. Yet, even here, engineers and visionaries see opportunity. Each challenge is an invitation to innovate, and laser communication stands as proof that human ingenuity can transform obstacles into stepping stones toward progress. Rather than viewing bottlenecks as setbacks, the scientific community treats them as fuel for breakthroughs, demonstrating resilience and creativity time and again. So what makes laser communication different? Instead of radio waves, which are broad and spread out as they travel, lasers transmit information as concentrated beams of light. Think of it this way, radio is like shouting across a crowded room where noise and distance drown you out. Lasers are like whispering through a laser pointer directly to someone's ear. Highly focused, precise, and with incredible clarity. A laser can pack far more data into its narrow beam, making it not just faster but also more efficient. According to NASA, laser links could transmit 10 to 100 times more data than traditional systems. That's the equivalent of replacing a single-lane country road with a 10-lane expressway into space. Imagine being able to stream entire VR experiences from lunar outposts back to Earth, or researchers pulling down live holographic data feeds from spacecraft orbiting Jupiter. But here's the catch. Space is unforgiving. Light beams have to cut through Earth's atmosphere, which distorts and scatters them. Satellites orbit, spin, and drift. Spacecraft millions of miles away need perfect aim to hit a receiver on Earth that may be only a few meters across. For decades, engineers thought it was nearly impossible to maintain that level of precision at interplanetary scales. A wobble of a fraction of a degree could mean total data loss. But now, with breakthroughs in adaptive optics, tracking algorithms, and stabilized satellite platforms, the impossible is becoming reality. Think of it like threading a needle across millions of kilometers while both you and the needle are moving, yet somehow with modern technology we're doing it. Each success is a celebration of human persistence, turning what once seemed fragile into something remarkably robust. The optimism behind these advances showcases how resilience paired with determination can unlock what once seemed unreachable. One of the most ambitious milestones in this journey is NASA's Laser Communications Relay Demonstration, or LCRD. Launched in December 2021, it's orbiting Earth 22,000 miles up, serving as the first ever long-term testbed for space-to-ground laser links. Picture this. 2 laser terminals aboard the satellite beam data back and forth to specialized ground stations in California and Hawaii. Unlike a short test flight, LCRD is designed to operate for years, pushing laser systems through storms, atmospheric interference, and orbital dynamics to prove they can work under real-world conditions. It's not a lab experiment, it's a dress rehearsal for the communications infrastructure of the future. Every single successful link builds confidence that future Mars missions won't be sending trickles of data but floods. And the results? Staggering. LCRD has already demonstrated data rates up to 1.2 gigabits per second, about the speed of home fiber internet, except it's coming from orbit. By comparison, many existing space radio systems are limited to just a few megabits per second. That's like comparing a garden hose to a fire hydrant. In fact, engineers estimate that a single laser link could transfer an entire Blu-ray movie from orbit to Earth in under a minute, something that would take hours over traditional systems. For astronauts and scientists, that kind of bandwidth could mean the difference between delayed decisions and immediate responses. The implications ripple across every corner of space exploration. Imagine astronauts on the Artemis missions live-streaming ultra-high-definition video from the moon back to classrooms on Earth with almost no delay. Imagine scientists collaborating globally in real time, manipulating datasets pulled down directly from orbit. Picture a Mars rover streaming full panoramic video as it drives, allowing scientists to virtually walk alongside it in near real time. Consider the security benefits. Laser beams are so narrow they're almost impossible to intercept without detection, making them ideal for secure military and commercial applications in orbit. Beyond our solar system, laser communication could be the only way we ever talk to probes exploring distant worlds, where every bit of efficiency matters. It's not just NASA investing in this future. The European Space Agency, private companies like SpaceX, and even defense organizations are racing to integrate optical communication into satellites. Google's Loon project, which once sought to deliver internet from stratospheric balloons, experimented with optical crosslinks. Starlink, SpaceX's sprawling satellite internet constellation, has begun equipping satellites with laser terminals to connect them directly, bypassing ground stations and cutting latency across continents. The result? Faster connections between continents, near real-time satellite relays, and a preview of what the same technology will do for space exploration. In other words, the same laser technology revolutionizing deep space could transform your home internet too. Of course, there are challenges. Clouds can block laser beams, turbulence in the atmosphere can distort signals, and while radio waves spread wide enough to be caught by massive antennas even when aim is imperfect, lasers demand precision. Lose alignment by even a fraction, and the connection drops. But every challenge is also an opportunity for refinement. Engineers see these obstacles as puzzles to solve, and each solution makes the system stronger, more reliable, and more inspiring. That's why redundancy is key. Multiple satellites, multiple ground stations, and hybrid systems that can fall back on radio when needed. Engineers envision a future network where satellites hand off laser links from one to the next in seamless chains, ensuring coverage even if a single path is blocked. In the long run, expect a marriage of technologies: radio for broad reliability, lasers for high-speed backbones, working together in a layered network that highlights our resilience. Framing each difficulty as progress in the making keeps the vision positive and forward-looking. This layered approach is critical as humanity sets its sights beyond Earth. Consider Mars. The average delay for a radio signal traveling from Mars to Earth ranges between 5 and 20 minutes. That's just physics. Distance dictates the time. Lasers can't change the speed of light, but they can change how much information makes the trip. A laser link could turn what is today a trickle of images into a flood of real-time video and diagnostics, compressing years of exploration into months. NASA's Psyche mission, which launched in 2023, is already carrying a deep space optical communications experiment to test exactly this kind of system on its journey to a metal-rich asteroid. It's the first interplanetary laser communication test in history, and its success will shape how we talk to spacecraft for decades to come. Midway through, let's pause and think big. The shift to lasers isn't just a NASA upgrade, it's a fundamental rewiring of how humanity talks to its machines across the stars. We are, in real time, rewriting the nervous system of space exploration. And if you're fascinated by this glimpse into our future, subscribe, like, and turn on notifications because the next wave of space tech is accelerating fast and you won't want to miss it. Now let's zoom out to the big picture. Humanity is entering an era of mega constellations, lunar bases, and eventual Mars colonies. These aren't distant science fiction dreams, they're the explicit roadmaps of agencies and companies right now. But every colony, every base, every autonomous rover depends on communication. Data is the lifeblood of exploration. Without robust high-speed links, science slows, safety is compromised, and progress stalls. Laser communication is the circulatory system that will keep this next generation of space projects alive and thriving. It's no exaggeration to say that without it, our dreams of living beyond Earth would remain science fiction. Think about astronauts in orbit running medical scans, transmitting them instantly to doctors on Earth for diagnosis. Picture climate monitoring satellites streaming raw data without delay, empowering scientists to model weather patterns more accurately and save lives during disasters. Envision schoolchildren logging into real-time feeds from the moon, sparking a wave of inspiration as vivid as Apollo once did. Even businesses could benefit. Imagine corporations beaming financial, navigational, and industrial data across continents through orbital laser relays, bypassing undersea cables altogether. This is not abstract, it's the world that laser technology makes possible. But the dream doesn't stop there. Engineers are already exploring quantum communication, where entangled particles could one day transmit information even more securely and perhaps instantaneously. Many of the building blocks for quantum systems overlap with laser communication: optical fibers, photon detectors, coherent light sources. Today's investment in lasers may lay the groundwork for tomorrow's quantum internet of space. In a very real sense, laser beams could be the stepping stones to something even greater. Instantaneous communication across vast distances, reshaping everything from commerce to colonization. Highlighting these possibilities connects the breakthroughs of today with the boundless opportunities of tomorrow. Still, like every frontier, the road will be uneven. Expect delays, cost overruns, and setbacks. Adaptive optics will need refinement. Atmospheric interference will remain a hurdle. Scaling up from demonstrations to global networks will demand international cooperation, standardization, and trust between nations. Yet with each hurdle, we advance. Each problem solved is another triumph of creativity, persistence, and collaboration. Remember this: radio took decades to evolve from scratchy beeps to today's seamless networks. Lasers are on a faster trajectory, with breakthroughs stacking up every year. The pace of progress is accelerating and momentum is on our side. As the LCRD continues to operate, each gigabit of data it streams back is not just a technical test, but a glimpse into a future where Earth and space are linked by shimmering threads of light. These beams will carry our science, our stories, our emergencies, and our triumphs. They'll bridge the void between worlds, making the solar system a little smaller, a little more connected, and a lot more human. One day, when humanity looks back on its first true steps toward becoming a multiplanetary species, laser communication will be recognized as the unsung hero that made it all possible. So the next time you look up at the night sky, imagine invisible beams of light crisscrossing the heavens, carrying humanity's voice across the stars. That's the promise of laser communication, to transform space into not just a frontier, but a connected community, a vast web where information travels at the speed of light itself. What do you think about laser technology shaping the future of space communication? Drop your thoughts in the comments below. Ready to explore even more groundbreaking innovations in space? Subscribe, like, and turn on notifications. Because the next great leap is already on its way. This is Tech Mythos.